Yeah, so I'm based down at the National Oceanography Centre, and I'm just going to be discussing some of my PhD work, which looks at the geochemical variations that we see at the scale of an individual seamount. So a quick overview, because we've gone over this morning, especially in the keynote talk, but obviously in the future, as we shift towards a more green energy-based technology, so things like solar panels and wind turbines, and with the increase in electric vehicles, where obviously these are all really material-intensive technologies. So in the future, we're going to see a shift in the resource base, which has very large implications for the raw materials that are required. So for example, we see with the growth of electric vehicles, so we saw this morning that an electric car contains up to 10 kilograms of cobalt, and that goes up to about 23 for a Tesla if you want a fancy car. This is also predicted to correlate with a huge increase in the cobalt demand in the future. So current terrestrial mining, we won't meet this future demand, but one opportunity is potentially the deep sea. So one way to define the critical elements that we're interested in is to look at the economic importance along the bottom. So this is, for example, how important it might be for an innovative or disruptive technology. Another factor that we need to really consider is the supply risk. So this can be something in the idea that geology isn't fair. So the distribution of elements over the globe can really distribute the elements in specific countries. So for example, rare earth element concentrations in China. And another aspect of supply risk could be something like the potential political conflicts in those regions. When we consider the deep sea, if you can see in this diagram, I've just highlighted some of the elements that are concentrated in deep sea ferromanganese crusts, highlighted in green. So the key of these is cobalt, which we see in really high concentrations and which is really important for electric vehicles, and also tellurium down here. So that's in particular important for things like cadmium telluride solar panels. So ferromanganese crusts, these are formed largely of amorphous iron oxyhydroxides and manganese oxides. They encrust hard substrates, and we find them extensively on seamounts on the seafloor, and they form really slowly, so precipitate at about 1 millimetre per every million years. We've actually extensively sampled crusts throughout all the major ocean basins, and historically, since the 1970s, we've focused mainly our studies on dredge samples, and we focus mainly on the Pacific Ocean, so a region called the Prime Crust Zone in the North Pacific, where we see some of the highest cobalt concentrations. In the past, because dredging techniques have dominated, it means that we've been limited in terms of the spatial controls that we have on some of our sampling. So just to introduce the Marine Tech project, this is a multidisciplinary project that we're undertaking with a number of different institutes. So we've got the BGS and also the Oceanographic Institute down at the University of Sao Paulo and HR Wallingford. So this was an opportunity for us to investigate at the Seamount-scale a northeast Atlantic seamount. So we had the chance to bring an automated autonomous vehicle, the AUV, and the remotely operated vehicle, which also had a drill mounted on the front so that we could get real in situ sampling. So our focus is a seamount in the northeast Atlantic called Tropic Seamount. So this lies between the Canary Island Seamount province and the sub-Saharan seamount chains just off the west coast of Africa. So we know for our resource estimations that a lot of things that feed into these are assumptions on what controls the occurrence and the morphology, and also thickness is currently used as a major indicator of a potential deposit side. In terms of the factors that can affect this variance, we actually think that things like depth, environment, whether we might have had diagenesis, so for example, phosphoritization events, and whether we have active crust growth and crust growth rates, these all feed into these models, but are something that are actually very difficult to constrain. So the first thing that we did down at Southampton is I've looked at mapping seamount environments from over 300 hours of ROV footage. So this gives you tracks along the limbs of the seamount, and it means that you can look at the in situ environment. So focusing on things like pavement environments, which will obviously be a key target for future mining. And along the flanks, we've also got low bait environments that are encrusted low bait material with actually very thick crusts. And it's also about defining areas where we don't see ferromanganese crust coverage. So we've got extensive samplings. And in this diagram, you can just see the sort of distributions that we can map from these ROV video tracts. So for example, on the summit, we see a concentration of pavement environments, which is obviously key. So the summit of Tropic Seamount, we see at about 2,000 meters, and this goes down to 4,000 meters at the base. Within the center of this seamount, we actually see a large accumulation of sediment. So what lies below this, it's likely that there is actually sediment, ferromanganese crust, that lies below a very shallow sediment cover. We've seen this from our drilling. The main issue is that in order to try and predict metal concentrations, we need to be able to do this even for covered material. Along the flanks, you can see that actually we've got the majority of crust exposed, and we've actually sampled quite thick crusts. The main issues that come up here are that there will be the mining technology and capabilities in the future. In order to gain a better understanding of the kind of geochemistry that we see at Tropic Seamount, this is just a box plot summary of some of the key target metals. So the solid bar in the middle gives the median for each of those elements, and then the upper and lower edges of the box give the upper and lower quartiles. We've also got some of the ocean basins taken from summaries from Heine et al., just to give us a comparison. So we can actually see for things like cobalt, we see about 0.5% of cobalt concentration within the ferromanganese crusts at Tropic, which is pretty significant if you think about the kind of material that we mine on land currently for copper porphyries and larger deposits. It's a significant increase in concentration. But actually what we see at Tropic Seamount is it's pretty standard for an Atlantic seamount, and in most cases, the Pacific Ocean crusts from the prime crust zone, for example, have generally higher concentrations. But places where Tropic actually has higher concentrations than the Pacific, these include for elements such as cerium, lithium, and molybdenum. So to investigate this a little bit further and how these crusts might have formed, you can look at different trace element ratios to determine the genesis. So looking at the bulk chemistry of our samples, we can see that we've got really distinctive rare earth patterns, so a positive cerium anomaly and a negative yttrium anomaly that suggest hydrogenetic formation. So basically they precipitate directly from seawater and they lock in that seawater signature just at far higher concentrations because they form so slowly over millions of years, and they've got really high surface areas. You can also look at the other trace element ratios, for example, so iron and manganese when you compare it to the nickel, copper, cobalt. And you can see nicely that all of our samples fall well within the hydrogenetic field when you look at the bulk chemistry. So ideally, hydrogenetic crusts are thought to be the key target elements because what you look at is the manganese and iron ratios, and they can give you a bit of an indication of the kind of suite of elements that you might see. So a higher manganese proportion is associated with higher copper values. Cobalt values, sorry. So we can also look at some of the trends at depth. So what we see in the Pacific, you see quite a strong correlation in dredge samples in the concentration of different elements with depth. And we see exactly the same thing at Tropic Seamount when we sample on a far higher scale. So we see, for example, with the iron-manganese ratios, we have higher manganese-iron ratios at the summit. And this is actually, it's quite a promising thing. So for mining, in terms of technology, the summit is flat. It will be the most easiest to mine, and it's the most shallow. And they also have the most promising crusts. It's interesting to note that this depth trend has in the past been associated with the location of the oxygen minimum zone. So in the Pacific, we have really strong oxygen minimum zones. It goes down to truly suboxic levels of about less than 0.1 micromoles per kilogram. In the Atlantic, we don't really get below 40 micromoles per kilogram, and at Tropic, we don't really get below 100. So what we're seeing is that at Tropic Seamount, we have quite a well-ventilated area in modern oceans. So what kind of implication might this have on the formation of ferromanganese crusts? Because what you want is a strong gradient for the oxygen minimum zone so that you can collect all of your manganese ions, and they have time to form colloid complexes. And then the upwelling of oxygen-rich waters from depth triggers the precipitation of crusts. So if we don't have this really strong gradient, then what's really controlling the variation in our depth profiles? So another example where we see an even stronger correlation with depth is for cobalt. So here, this is a Spearman rank correlation. So we've got 64% and 77% for tellurium, which is much more enriched in Atlantic basins. What's really interesting is that while the shallow samples look to be really interesting for mining, we don't really fully understand the spread in this data. And in order to do really strong resource estimates, we need to understand what controls the variance at specific depth levels. So what's controlling this spread on the summit samples in the concentrations of tellurium and cobalt, for example. And it's highly likely that these are probably local processes which the sampling campaign that we undertook will help us to unravel. So one way we can do this is to do correlation analyses. So here, you won't be able to see all of the elements, so I'm just going to go through them. But any elements that have a strong negative correlation are highlighted in red, and any with a strong positive correlation are highlighted in blue. So this just gives us an example of the correlations that we see between different elements. And if you look at a factor analysis, for example, for these, we can see that most of the variance in our geochemistry can be about 70% of that variance is actually encompassed in 4 main factors. So, for example, if we look at what elements are also co-varying with manganese, which is a key thing for some of our target metals, we see things like molybdenum, tungsten, zinc, barium. Actually, when we've investigated further, we've found that as opposed to the assumed hydrogenetic signal, where you might assume a much closer correlation with things like tellurium, you actually have more of a diagenetic correlation. So we know that diagenesis is really important at tropic seamount because we see extensive phosphatization, and we know that this can change the elemental ratios for different elements, in particular for lead. For iron, what we find is that we see more of a correlation with things like zirconium and vanadium, and in particular the rare earth elements, and especially the light rare earth elements. And traditionally, what you would want to look at for iron oxyhydroxides is the hydrogenetic signal, because this gives you an indication of the resource wealth. But really what we're seeing here is that the iron correlations are being muddied basically by external inputs into detrital factors. So this is being found to be a really important influence at tropic seamount. One way that we can investigate this further is to look at just the surface chemistry. And in order to do this, we need to try and figure out where we have crusts actively forming or where we have surfaces preserved versus where we have old crust exposed and eroded. And this can be something that we then correlate with some of the hydrographic modelling that was carried out by H.R. Wallingford. And this gives us an idea of the sort of potential local in situ processes. So on this map, you can see that areas where erosion has happened are highlighted by the circles in red, and we've done this by analysing the surfaces of ferromanganese crust samples under the SEM. And basically you see that at the summit and along this eastern spur, you get high rates of erosion down at all depths and at the summit surface. Whereas on the southern and western limbs, you get more preserved surfaces. So these would be the samples that we want to target to try and analyse what kind of local in situ drivers we can pull out of the signal. What we find is actually this fits really nicely with some of the modelling that was done by H.R. Wallingford. So you see that the flow energy is concentrated on this eastern spur and on the summit. And so it's thought that this formation of something called a Taylor column could be driving the erosion of ferromanganese crusts, and this means that the erosion is outpacing our crust formation. And we can see this in a historic record. So if you look through crust segments, you can see horizons of erosion. So it'll be a really interesting study to look back in the past and see whether we have a reduction in our crust coverage. So just in terms of outlook of how this study fits into resource estimations, we know that crust coverage is expansive, and we know that crusts have high concentrations of a lot of the target metals. The main issue is that they're incredibly variable on all scales, and we don't fully understand the controls on thickness and occurrence. So there are promising average concentrations, but really what we need in order to predict how we might exploit this resource in the future is a model of what controls the concentrations on the local scale. So factors that we've previously used really rely on these assumptions that then can be updated using our improved understanding, using specific, highly precise locations for our sampling. So thank you.
Thank you very much, Sarah. We have time for some questions for Sarah.
So, the erosion. If the erosion rate is exceeding the deposition rate, does this mean that these things will eventually disappear?
So it's a tricky balance. So in the traditional model of ferromanganese crust growth, the idea is that you need a threshold in terms of current speeds to have a cleared area, because if you have sediment cover and unconsolidated sediment, that's not a stable surface for ferromanganese crust to grow on. So it's a fine balance between having something where you have exposed substrate, but also you're not removing your crusts through abrasion. So that's something that we really want to quantify, and we're getting more models drawn up, hopefully by HR Wallingford. And the idea is that we do see in the geological record, crusts would be a great oceanographic record if they didn't have huge erosional events. That means that their history and timelines are really difficult to quantify. So if we can look at the erosion rates of ferromanganese crusts, then we could say whether you have a promising resource. So it's similar to Dan's problem of mass wastage events. They occur on seamount, so we have promising crusts on the side. And it's a balance of whether the erosion rates are helping or hindering, basically. So